Get started then. Try to keep to the schedule. So we have an hour for James, and we'll have an hour for discussion with Thomas here in management and also in neurology and neurosurgery. I've been for about 11 years, but I'm not allowed to do brain surgery. They're very strict about that, which I find reassuring. I do leadership stuff, and I'm on the faculty at Oxford. I did work with the Oxford Medical School, and I was at the Oxford Business School, so I can do it. Would you like me to do the whole talk in an Oxford accent? They made fun of me. I learned how to do British accents, but I'll stick with my Canadian. Do you understand us when we talk, James?
Well, just give me a go. Amp it up.
Okay, so delighted to have James join us. He's a professor, a director of the Knowledge Lab, and professor of sociology at the University of Chicago. He was mentioning yesterday he was doing a bit of teaching at the business school, at the Booth School at the University of Chicago. Delighted to have us join us, and very much looking forward to his talk on technology, change in medicine, centers, and markets.
Thanks. So I'm James Evans. I'm in sociology, and I run a little center at our Computation Institute, which is between computer science and Argonne National Lab, and I also I teach in our business school. I mean, this is obviously the conference thing. This is, I changed my title just because I wanted to kind of pack in a couple of other studies that I felt like when I really kind of read through the other papers and talks I wanted to highlight and bring into part of the discussion. So tiny teams disrupt, that's study 1, chapter 1. Fragmented fields persist, and by this I mean findings persist, and it's in a particular case in the context of drug-gene interactions, or drug-cDNA interactions to be particular, and abnormal audiences, right? So people who actually are both speaking from and drawing from atypical combinations of audiences end up driving advances in biomedicine. Each of these are kind of a separate study that I'll talk about in sequence.
James, do you mind if they ask questions during, or would you prefer towards the end?
I'm happy to engage questions throughout, both clarifying and fundamental oppositions or empirical inaccuracies, or So the bigger the volume, the better. So I run this little center, which is really focused on using large-scale data, machine learning, intelligent crowdsourcing to kind of represent scientific, biomedical, and other kinds of knowledge and preferences, to understand it, to do kind of a big data science studies, if you will, and then to kind of turn it around as statistical instruments to generate hypotheses. I'm skeptical, for example, that we actually know something about the process of innovation in the sciences if by taking into account collective biases that we can't do better. Can't do better, that I'm dubious that we actually have any clue about how that process is occurring. So the first chapter, tiny teams disrupt. So lots of people in the past have talked about how solitary researchers and small teams are shrinking in areas of science, large teams are flourishing. This is nowhere more true than in biomedicine, so this is just kind of a trace across science, engineering, social sciences, even the humanities. It's almost imperceptible, but it's there. Team size of growth in publication. So here's the biomedical case. So this is Medline, so this is about 18 million papers, and we see basically the kind of growth of authors, the papers themselves, chemicals, diseases, and specific methods, which are annotated by a small team at the National Library of Medicine of postdocs and curators. If we actually look at the number of things to which each of these things are attached, so think about the degree, if you will, of a disease as a function of the number of papers in which it shows up in every year, then we see that there's a dramatic change that's taken place over the context of this period, and these are including back annotations to the 1950s and before. So the average disease, for example, has about 30 annotations, for example, in 1950, and it has about 200 annotations in 2010, right? So the average method is kind of more dramatic. It's got about 20 annotations in 1950, and on average it has about 1,000 annotations in 2010 per year. And so you can see, of course, certain approaches become much more central, and others are much less central in this space. Now, within the context of a particular paper, we see our own little transformation. So we have the rise of basically the number of persons per paper, right? So it kind of moves from 1.5 5 to about 1, 2, 3, 4, 5. And it actually moves in lockstep with the number of methods, right, that are used. So basically, we're adding and also with so basically the number of studies. So it's like a labor theory of value of papers. You know, we kind of we double the number of methods over the context of this period, and we basically slightly more than double the number of investigators. You know, so investigators in this context are effectively one-trick ponies. And if you look at this world in this way, which is to say as an evolving hypergraph, right? So imagine that every paper is just a collection of its contents, right? Of persons, medicines, the diseases themselves, and maybe chemical traces. Everything in this network is almost at maximum distance to, right? Everything is a friend of a friend in this network. Everything's relatively close in this network because I can connect to you as a function of, using the same method, studying the same disease, being involved in the same institutional setting, etc. And for that reason, it turns out that some of the methods that I'll describe later are required to actually analyze how innovation takes place in this kind of a space. Okay, so why are teams growing in the context of biomedicine, but also elsewhere? Who knows? But that hasn't stopped investigators from talking about why that's the case. Specialization of scientific activities. So maybe it's technology. So maybe it's communication, transportation technology. It's easier to get to the Gordon Conference. It's easier to kind of hyperlink ourselves together. It could be that knowledge communities are increasingly large and connected as a function of those advances. And it could be, and this is the claim that I question, although I'm open to, the complex modern problems fundamentally demand interdisciplinary teams, people who come from different kinds of backgrounds. What's actually been tested historically is that big teams have clear benefits for the members of big teams. So they generate more citations, it's more likely to receive funding. You have increased likelihood for promotion and reward. And I can show this. I have, for example, all of the NIH data for funded and unfunded grants over the course of the last 35 years. And so we can see, for example, precisely what it is that it takes to get onto a panel, and then conditional on being on a panel, what it takes to get a grant. So there's little evidence presented for why it is or whether collaboration is always a good strategy, a global strategy for the kind of emergence and development of knowledge. And so this is just an articulation, past articulation of these team citation benefits. So I'm just I'm trying to look at teams in a very simple way and look at their relative contributions to biomedicine, but also to other problem areas. And I'm going to basically kind of have the hunch, that small teams may be more involved in problem creation, and large teams may be more effective at problem solutions and developments. We'll see. And there's a whole kind of social psychology literature that surrounds this idea that people behave differently on small versus large teams. So people may expend less effort, engage in fewer differentiated tasks, may assume less responsibility for tasks. There's a whole host of things that suggest that they may not involve themselves in the same higher order organization that we might imagine could take place in large teams. There's also some generative research that's relatively unequivocal that suggests that people generate more ideas in small teams. They're less likely to reject internal viewpoints in small teams. There's a fair bit of work that looks at, this is the result of a study that Kareem Lakhani at Harvard Business School ran with his innovation lab in the context of, there are these programming tasks which are often put, some of them are biomedical, some of them, in this case, this was a NASA set of programming targets. And they basically created an experiment where they put people either in a wiki condition, where everyone had available to them the advance of everybody else in real time, and a kind of competition condition in which it was only revealed at the end what the best answer was. And what happens in the wiki condition is that there was what you'll call in optimization literature hill climbing, right? So basically, anytime anyone made an advance, everybody swarmed to the last advance and then kind of climbed the hill, which is fine. If it's a simple landscape, which is to say that if you keep climbing that hill, you're going to get to the peak. If it's a complex landscape, which is to say that if you're on some local peak and you kill the diverse approaches, which may have been harder but may have had a higher ultimate payoff, then, and that's exactly what they found, is that basically in simple tasks, wikis did faster, they were more emotionally rewarding, they more people stayed recruited, but for complex tasks, they performed less well relative to essentially competitive seeds, where people were performing and climbing these various hills in this complex discovery landscape. There's also, and this is other work of mine, this work on the Linus effect, where more contributors generate articles, for example, in the context of Wikipedia, that tend to be more neutral in content, right? So you kind of have a washing out of these effects. So this is work that we've done where you can instrument basically the degree to which people have left or right political leanings in the context of Wikipedia editorships, and you see as the number of editors goes up, the average kind of political alignment and political kind of radicalness of these pages dramatically goes down. And then there's also kind of an economic argument that small companies are more likely to undertake new untested opportunities. They have more to gain and less to lose, right? Large companies have more to lose and less to gain. This is this kind of greater demand or an ongoing stream of success to pay the bills in the context of individual labs. And it turns out we find some pretty strong evidence for this in the context of biomedicine. And it also, there might be greater perceived risk to reputation from failure and censure. I think this is probably, I know it's not a biomedical example, please don't be offended, but this is the LIGO experiment that yielded the 2017 Nobel Prize this fall by Kip Thorne and colleagues who designed this huge laser interferometer. It is a remarkable experiment and probably perhaps the most conservative experiment of all time. So it's 1,069 authors on the paper testing a 102-year-old hypothesis. Took them about 28 years to calibrate the instrument with a commitment that any finding other than the theoretical expectation of general relativity would be seen as a miscalibration error, right? So the only thing they could find was the positive affirmative finding. It's a remarkable scientific achievement, but it's probably the most conservative experiment of all time. And in fact, there's a really kind of interesting case in contenders for the money. So this is Weber, who was University of Maryland, going back to physicist who developed the maser and was influential in laser technology, who argued that you could basically do this. Initially, it was about $1 billion project, but this initially $324 million grant for pennies on the dollar, for like $500,000. And the only way in which they could really receive the funding was to completely trash Weber's reputation before Congress, which they did effectively and received the money and support to run the experiment. One other possible consequence is that basically you can imagine that for large-scale projects, if you're solving an existing problem or refining an existing design, it might ameliorate risk as there's a market for these solutions. So if you pick a big hit, if you pick last year's Nature biomedical publication, then there's a market. The people who cited or were aware of that publication are also prepared essentially for related efforts, whereas if you're generating a new problem, a new design, there is no existing market. It may take some time for that market to develop. And so I think in some sense, this may be part of the story with respect to the kind of uptake of particularly radical approaches is just the relative size, really, of the conceptual market space, people who are prepared to receive this. So I think that the question of this study is really what if small teams were important for biomedical discovery and invention, and I would say one of the unfortunate challenges is that really NSF, NIH, and DOE, I know the U.S. landscape, I don't really know the CAIHR and the other, the Canadian landscape, but I work closely, for example, with NSFC, China's National Science Foundation. All these institutions are really promoting large-scale teams in a dramatic way. They're incentivizing them. They're trying to push and instrument them together in places that, well, you'll see. It certainly will have a consequence for the unfolding of science and technology in these contexts. So I'm going to just measure kind of 6 things. I'm going to look at some consequences of large versus small teams. It's, you know, this is these are simple measures, and in fact, you could reinvent all of these. One, I'm going to look at kind of the disruption of the invention, and I'm going to define that in just a moment. I'm going to look at the relative impact, and I'm going to look at the delay of uptake. And then I'm also going to look at the associated search. Oh, I'm sorry. Okay, so how do I measure disruption? I'll have another slide that schematizes this, but it's basically the likelihood that you tend to eclipse the things that you build on, right? So if everything in the future cites you and they don't cite the things that you build on, then it's perceived that this is a break from the past. And there are a bunch of different ways to operationalize this. It doesn't matter which one we pick. Delay, we're just actually measuring it as the convexity of the citation distribution graph over time of the papers, but we also look at biomedical patents, all patents in general. We look at software. We have about 80 million cases that we're kind of looking at, which are highly consistent with the biomedical case. And then just, you know, the impact, the number of citations 5 years out. So disruption, we're basically looking at in this context. So you can think of this central circle in these cartoons here as being a paper, an innovation that builds on something from the past, and you can imagine different contexts. One context in which everything in the future forgets the past, and they only attend to the core innovation. In other cases, you effectively advertise for the past. You know, so basically everything that builds on you builds on what you built on. They acknowledge the pass-through contributions of those things before. And so, so here are just some kind of cartoons. You can see this is a core biomedical patent, and you have a host of things that are kind of citing this in the future, and some of them cite the past, some of them don't. Here's the cartoon. You can imagine on the one hand, you know, this thing attracts everything. It's seen. So, for example, you can think of like, you know, the motherboard comes along, which cites, you know, a transistor patent, but people are now using this itself, you know, standalone component, versus a case in which you're consolidating the world. You know, you basically are advertising for the things that you build on. And so you can look at this. We look at this in the context of, I have a postdoc who likes visualization, so he built feather versions and green tree versions. This is the one that's under review at Nature right now. Where we kind of, it turns out it's a very different spectrum. So these are all papers that have roughly equivalent numbers of citations, but they have dramatically different impact in the scientific landscape. The one to the left is self-organized criticality. Nothing cited their forebears, whereas the Bose-Einstein condensation was also associated with the 2006 Nobel Prize. It's a substantial paper, but it really advertised Bose-Einstein condensation as a theoretical construct, as an empirical construct. So here's, for example, Columbia's axle patents, right? So the process for inserting DNA into eukaryotic cells, for producing proteinaceous materials. So this is this disruptiveness index, which actually dramatically increases over time. So the first few things also cite their forebears. Virtually everything thereafter in the patent site cites that technology, and in fact sought to license that technology. Turns out that citations in the patenting space are correlated at like a third, like about 0.3 with licensing revenues associated with those patents. This is in the bioagricultural domain. So this is Monsanto's Roundup Ready soybean. And it turns out it had precisely the opposite trajectory, right? So basically, as it became more important, it actually drove or was associated with the driving of citations to things on which it built historically. Okay. So, and then I also look at search behaviors. So how deep are teams searching into the historical past for the things that they build on? How popular are the things on which they draw? And how broad are the things that they draw upon? So do they cross many fields? Are they within one particular field? And so, anyway, so I can, these are simple measures. They're just sums, normalized. Okay, so I'm using biomedical publications in PubMed linked to the Web of Science, so I can kind of use its citation access. I use the U.S. Patent and Trademark database, although I'm incorporating European patents right now. And we also, just for fun, included basically a huge public software repository, just to see if the same things we were seeing in these other domains kind of held in other inventive spaces. And the key thing about all these three spaces is each of these technologies are making claims about things that they link to in the past. Now, I am, I just published a paper 3 weeks ago on PNAS that did a content version of citations to kind of diagnose how bad citations were as a measure of influence. And they're bad, but they're not that bad. So I can predict, for example, about 50% of citations in, for example, like the American Physical Society papers among its 8 journals, about 50% just as a function of language, when someone states something and the degree to which it reverberates in future papers. So it's certainly not capturing everything, and there are other dynamics, and now I can diagnose them and do in that paper, but it's but I would argue that it actually gives us a rich trace. In this case, not a bad, I mean, if it's 50% signal of the amount of discursive influence that a paper has, then it's substantial. So this is the number of artifacts, scientific artifacts that we're looking at. And so here's the story for scientific papers and patents. So from team members from 1 to 10 and from 1 to 100, we see on the left in the green a virtually exponential decay in the disruption percentile, right? And this is the percentile, right? So this goes from here about 30 to about 90%, right? And in the 1 to 100 case, it goes from about 1% to about 99%. So, which is to say that basically the number of persons, and this is so simple. It's such a simple. I mean, I'm literally just looking at number of authors on papers. That accounts for about 95% of the full variation of disruption in the context of these papers. And I'll show the same is true for patents and software. So it has a dramatic effect. There's a slight increase with the number of citations that these products get. So this is actually the raw number. So it's an increase of about 10% in citations with larger teams, and an increase or decrease of about 80 to 90% in terms of its disruptive percentile. And it turns out it doesn't matter where you cut this distribution. As it is the top 5%. You can cut it at any distribution. You can see the same pattern at any period of time that we've looked at over the course of the last 100 years. One of the things that's striking is that it interacts with impact. So really successful small teams are much more likely to be disruptive. Really successful large teams are much more likely to be amplifying formal work. This is the case where we look at the transition rate for different fields. So in biology and medicine, for example, you see the transition from where the average team of said size moves from, on average, kind of producing a paper that disrupts the space, which is to say that it drives disproportionate attention to its work relative to the things that it builds on versus the other. In medicine, it's about 3 is the transition point. So basically 1, 2, or 3 is kind of a break even. Above 3, it's very unlikely for the paper to be disruptive. And in biology, it's 1. I mean, it's it's hard to be disruptive. It's actually the guy who runs the archive at Cornell University. It's interesting. I asked him so that this is a preprint server for papers in math and physical sciences, also in quantitative biology and medicine, are increasingly kind of going on this preprint server. And I asked him, do you do any quality control? Because you could imagine, crazy things would come out on this thing. And of course, and he's like, yeah, we do some quality control. I have a Bayesian, naive Bayes model. I said, what are the predictors of things that basically get picked off as crazy? to avoid essentially bad press to the system. It's like, well, the three highest predictors are single author, submitted on a weekend, and high proportion of citations to Newton and Einstein. Those are the three core elements. So those really are crazy papers. I mean, so small team papers are much more likely, as you'll see in a moment, to search out they're likely to build on unusual things, to build on things much deeper in the past, and are much less likely to actually fit within the current of current biomedical doctrine. It turns out, you can imagine there's just different science going on. Small teams are just doing different science than big teams. 66% of the effect is within person. And 66% of the effect is within person when I'm just doing a non-empirical study. So I'm literally writing a review paper. I shift from doing a review paper with 3 people to doing a review paper with 4 people, and we see, again, 2/3 of the effect. We see, that full effect when we also control in a loose way for content. So we basically build these rich autoencoder models which kind of take into account really rich subfields in the space. We use those to control for the effect and find that, again, within person, even within kinds of study, we capture 2/3 of that effect. Not all of it. So some of it clearly is a function of some, kinds of science are just associated with larger teams and smaller teams, but that's not the majority of this effect. This is the delay. So we use that convexity indicator of citation. It's named the Sleeping Beauty Index based on a PNAS paper a couple of years ago. It's a very simple but pretty measure. And so this is the relative, it's dramatic decay. With team size from 1 to 8, we're basically moving from almost an 80th percentile in the Sleeping Beauty Index, which is a delay in uptake for like 7 or 8 years. So about half of the, of the effect that one might see in the context of other innovation studies, to a delay of like 1 year, 1.5 years. So what happens is, on average, in biomedicine, but also in these other sciences, basically, large teams are picking off as targets, as things that they're going to build on last year's papers and projects, on average. And all their impact happens immediately, right? Because that market that wrote those papers, that read those papers, that cited those papers, is available, basically, to jump onto their incremental developments and adjustments on that context. These smaller papers, these smaller teams are like, wandering in the wilderness. They find something that's potentially interesting, but may not connect with the kind of socio-technical inputs and outputs of surrounding science. It turns out this is a huge global effect in the sense that, for example, if you want to maximize the kind of impact of a set of teams over time, in 5 or 10 years you'd pick large teams. At 20 years you'd pick small teams, right? So the delay is actually enough that it reverses the direction, the average direction of impact per investment. And certainly if you want to look at 50 years out. So this is the difference in the search, right? So the difference in reference age that kind of drops with team size, and the reference popularity, which jumps with team size, about 30 percentage points. This is the context of patents in terms of disruption versus citations, and this age of search, this is the context of software in terms of disruption and citations. Okay, so this is basically where we look at awards, not just percentiles of impact in terms of the citation space. So in the Nobel Prize for Medicine and the Nobel Prize for Chemistry, you end up seeing really big jumps in disruption, relative jumps in for smaller relative teams. So you basically have far fewer teams that have zero disruption and more teams that have either are amplifying or disrupting effects. And let's see. This is, it turns out, the opposite for funding decisions. So we linked on funding from the US, Canada, Israel, Germany, China, a couple of other countries. We identified funding acknowledgments over the course of the past 12 years to these assertions, and it turns out that they do exactly the opposite. So we're funding the most conservative work. So you can see the kind of the peak in that conservative work. So just a taste of the NIH work that suggests something about what it is that we're investing in. So this is basically kind of first and second stage in each of these panels, first and second stage review. So basically, if you're reviewing grants that are received, these are all R01 grants over the course of the past 40 years. Yeah, 38 years, right, to the beginning of the 1980s. And so these are the degree to which features associated with the PI and the grant itself, which is to say its administrative structure. So is it a renewal, basically, or is it an invited resubmission, versus the content? And what we see is that there's a tiny impact which is associated with content in getting onto the review panel, and then once the degree to which you have a history of significant collaborations and a high-profile research past, so high citations to kind of former papers, you can basically see that's the thing that gets you onto the panel. That accounts for about 85% of the likelihood to get on the panel. Once you're on the panel, people pay more attention to the content. So there's kind of a threshold system where it's very difficult, in the discussion of peripheries for people who are outside the system to get onto these panels. We have some other work. The colleague of mine who wrote this is writing this paper with me. This hasn't been published yet. It's under review. But he had a science paper last November, which also showed that if you're successful in the past, then you're likely successful with your other related projects within 3 years of that first project. So we can't predict when over the course of the scientist's life course when they're going to be successful. So it's not less likely conditional on productivity of being late in the career or early in the career, but conditional on you being successful at one moment. We can predict with almost certainty that your next most successful paper will be within 3 years of that first one. So you kind of you tap into a nerve, you find something that's significant to the community for whatever reason, and then the work that builds on that or surrounds that is the work that's most likely to be appreciated. Which is to say that this is a terrible strategy for funding successful future science. I mean, I cannot find any defense. No one at NIH defends this, and we're working with the NIH on this. It's not. I'm an employee of the NIH to get this access to this data. But I think, it may fulfill other functions. It certainly feeds mouths. It may produce human capital. But there's no question. There's no defense of this as a method of really kind of pushing the frontiers of science. I won't talk about this given our time. This is interesting. So this just shows basically two opposing interaction effects with the effect that we find. So this is the disruption percentile effect. And this is basically, this is the Nobel Prize likelihood. And so what you see is small team Nobel Prizes or Nobel Prize associated papers end up being more disruptive per person. And on average, the large team Nobel Prize papers end up being more amplifying per person, whereas funding has exactly the opposite effect. So it actually, we don't know exactly why this is the case, but it seems that small teams that receive disproportionate amounts of funding look like large teams. So I don't know if they tie themselves to the mast by committing to the same kind of early project that they proposed, or I'm not exactly, I don't know why that's the case. But the basic story is that kind of tiny broke teams tend to disrupt in this space. This is like an afterword of that. The other parts are smaller, and I'm going to try to finish them quickly so I can get your thoughts. So we also did something where we tried to pull apart papers in terms of what I call probably offensively, I'm sure this won't make it into the published paper, brains versus muscles. These are self-attributed brains versus muscles. So when you have to say, for example, in the post-acknowledgement contribution section, oh, you know, typically the corresponding author of the paper says, I was responsible for conceiving and designing of the study, et cetera, et cetera, et cetera. And then somebody else, you know, was involved in performing assay X or statistical analysis on the results of X experiment. So the designers, writers of the study are brains. In this context, those who are attributed specific experimental procedures are muscles. And it turns out, and this suggests, I would say, the economic influence of this rather than just the social psychological influence, that it really ends up being about the brain to muscle ratio, which is to say muscles cost money. And so we can show that there's a huge effect in the kind of the number of people who are performing these experiments and the budgets which are associated with these studies, and that even controlling for team size, that this brain-muscle ratio accounts for many of the same things that we saw in these other contexts, which is to say, what's really driving the small team effect or one of the things that's clearly involved, highly associated in all these contexts, is essentially the cost and the experimental commitment, which is to say of these teams. They're less likely to and less able to wander. So this is done with a couple of colleagues, Ling-Fei Wu and Da-Xun Wang.
So you just three, though?
What?
Just three people. So you've been reading your own research?
Yeah. It was...
and no money, I assume.
Little money. They came later. They came later after we'd shown the initial results of our study. Then the Air Force funded some later work, which will certainly be much less interesting. So I'm going to whip through these other two things. Oh, gee, really quickly. Okay, so I'm not going to give details, but I'll kind of show effects. I'm happy to argue about them. Happy to get your insights. All this stuff is in process. I would say the findings are as firm as I can think of them, but they haven't been published yet. So your suggestions will be welcome and incorporated. So here we're asking this question about fragmented fields. So now I'm asking the question with respect to any particular biomedical truth claim in the literature. What's the effect of the centralization and the concentration of these teams with each other, right? So, for example, you can imagine the head of an influential center being the PI on many papers surrounding a particular drug cDNA claim, and that happens often in this case. What's the impact of those kinds of choices versus a decentralized or, in fact, completely fragmented community of different small teams that make that same claim? So is there any difference in truth value? And the reason we engaged in this study was we had a DARPA project to basically, pull, millions, tens of millions of claims from the literature about drug-gene interactions and use them to basically build these models which would drive experiments about optimal therapeutic cocktail combinations. And the problem was the literature was, a lot of literature was garbage. And so we were trying to basically figure out if there was an instrument in what I call the socio-technical production of the literature, which predicted the likelihood that particular papers would replicate. And it turns out there's a strong signal. So, okay, so that's our sparse versus kind of completely connected networks more or less likely to have claims robustly associated. The study design was simple. We basically took 75,000 drug cDNA claims from the literature in the past, and we linked them up to a huge high-throughput study. So this is the links L1000. It's about 1.4 million replications across dosages, time intervals, and a number of different cell types. And so we basically are kind of treating this, and there's all kinds of problems with that. We're treating this kind of final set of highly, massively computationally replicated studies as future truth, and we're basically saying, is there signal in the structure of these earlier claims that increases or decreases that value? And so you can see how scientists, and we also extracted from those papers not only the claims, but the techniques that they used associated with the claims, the citations that they drew upon to condition the analyses that they did based on those claims. And you can see more fragmented communities, more centralized communities, where more authors, or more of the papers shared authors, more of them shared methods, more of them shared citations, and more of them shared agreement. And there's some argument that multiple, empirical approaches might help us triangulate this. So we basically measured the kind of degree of social, methodological, and kind of prior knowledge independence, and then we measured these for all 51,000 unique claims. Each of one was associated with a community of many papers, and so we kind of stack these networks on top of each other, and we also look at the centralization of the scientific community. And I'm just going to jump to our, well, this is relatively important. So basically, if you share authors, then you do, with 95% probability, use the same methods with respect to a particular drug cDNA interaction claim. And you're even more likely to basically draw on the same citation resources. So you're performing the very same experiment effectively. So when you've got 100 papers that come from 2 PIs and their 7 students, then they're not 100 independent replications. And it turns out that this is what we see, is that, I'm just going to jump to our findings. We'll put all these things together to predict the likelihood that you replicate. So the nice thing is that science kind of works, which is to say that more people who make that claim are associated with a higher likelihood of replication. And that's a strong effect. So we have a Bayesian measure, and it improves the likelihood of replicating by almost 80% above random. So it's a huge positive effect. You have a strong negative effect for author centralization. So basically, the degree, which completely counters this effect, which is to say, if you have a highly connected community, many of these communities were highly connected, then it's no different in terms of the truth value of the claim than if one single PI, in one lab performed that experiment, which is about 8% more likely than random to replicate in the future. And so we can titrate that. Okay, final thing, and crud. Okay, I'll just do this really fast. Okay, abnormal audiences are associated with the drive of advance. So this is like the kind of the weirdest construction of the three, but I actually find it the most interesting. So just kind of maybe try to bear with me. Okay, so I'm trying to have a weird prediction task. Okay, again, forgive me. So I wanted to just predict all of next year's papers, or all of next year's patents, all of, and so by, of course, a paper, I'm not writing the paper. I'm conceiving of each paper in a very thin way as a bag of keywords. Okay, so I'm basically trying to predict all of next year's bags of keywords. That basically there are going to be 13 papers that study this disease with these 2 methods using this one chemical signature, right? And then for all papers, right? And so I did it in some weird machine learning way, so I basically, created some latent space, which is what people do now, and I let that latent space kind of move with Brownian motion over time, and then I pulled down a hypergraph at each point, which is an overlapping set of sets, which are these papers. And it turns out the dimensions that you induce to do that right, look beautiful. You can't even see them at all here. Okay, but they are, they're like tooth disorders, mouth associated disorders. I mean, they basically discover latent features which are associated with similarity. And then it turns out this is actually not right. So when we predict next year's papers, we're able to predict about 95% of next year's papers. Right? So I'm able to, and this is an AUC, so this accounts also for the papers that weren't published, right? And it's about the same for physics journals. It's a little less for patents. It's about 92% for patents. And it turns out you can do about the same if instead of contents, which are these keywords, you do contexts. And what do I consider context? Here I'm just considering context literally the journals that you draw from or that you cite. So just think of the set of journals that you draw on. You can think of those as, you're kind of wandering through some scientific communities, kind of pull on those things. And I can build a model that's identical to this, and it produces a prediction of about 95, 96% of the likelihood that we'll have 50 papers that draw on, the Annals of Internal Medicine and, each combination. Okay, and it turns out there's kind of a problem which is associated with this predictability. And the problem is that it suggests that last year's science almost perfectly predicts next year's science. No surprise, considering we've got PIs and inertial research teams, et cetera. But it also means that there's almost zero influence from the ebb and flow of pain and suffering associated with diseases, right? Because it can't influence. It's like. Maybe no one watched or remembers Seinfeld, but American comedy sitcom. There's no plot to the show, right? The show generates its own plot. People are standing in line, waiting to get into some famous deli. Like that's the whole plot. They're chattering, and that's basically, I think, what we see here is that basically science, or biomedical sciences in particular, kind of generating their own internal market or atmosphere of supplies and demands, which yield next year's papers, and we can show this both globally and also within the U.S. that this increase in predictability from last year's papers is associated with a decrease in predictability from last year's problems. And you can see this is I map on all major biomedical awards to papers, and in biomedicine in particular, you see this big bump. So these are different strategies for kind of connecting things in this space. These are kind of like bridging strategies, or I'm sorry, not bridging, but kind of where you're jumping, where you're introducing a new chemical. Those are highly appreciated. These are consolidating strategies, where you're connecting things which are already present in a subfield, but they're not connected together. And those are the things which are most differentially associated with elite prizes like the Nobel Prize and with most of these biomedical prizes, right? So the idea that the community that's generating the award ends up highly valuing connections between its elements, right? So it's an audience, it's the audience, it's, which is unsurprising why, for example, connections, highly cited connections between biomedicine and physics, for example, are much less likely to receive major awards. Okay, so contents and context. Again, this is dry, so I'm going to go really quick. But one of the things that's interesting is that they actually don't correlate. They correlate at like less than 0.1. Why? Because basically, so this is Medline. So when we've got a bunch of elements in our papers, we cite the ones which are familiar to our audience, right? So we're about 5 times as likely to cite journals which are associated with elements which is unsurprising, right? Because these are going to be this is our editor, these are our reviewers, right? We're much less likely to cite things that are far away, and in that PNAS paper I mentioned where we diagnose citations, this is exactly what we see, kind of a statute of limitations for citations. For patents, it's exactly the opposite. So you're more likely to cite things that are far away because there's no field, right? The benefit you get is actually from being distant from anything that's relevant to you. So then we've shrink wrapped this model of normal science and biomedicine, and then we take its inverse. I know it's so anal. We take its inverse. We take the paper which is the most unlikely to have shown up, right, next year, with this best fitting model of science that predicts 95% of next year's papers. We take the most unlikely papers, right, the improbability of the paper as a function of content and context, which is to say that it's, no one's combined things like that before, and it's completely inconceivable that someone could wander around through the literature and come across that collection of journals, right? And that improbability predicts almost 50%, about 49% of the likelihood of being in the top 1% of citations, right? So we weren't building a model that did that. We got that for free, which is about, it's about 6 times as much as anyone else has predicted of basically high-profile citations. So basically, if you're drawing on these very unusual audiences, and we're in the process right now of figuring out what kind of weird career trajectories are associated with the people who are pulling together these unusual contexts to create work which again, I mean, just the substance of the work alone predicts this, anyway, this likelihood that you'll be highly attentive in the field. Anyway, conclusion. Small teams disrupt biomedical science, big teams develop existing science and technologies. Fragmented fields comprised of small, non-overlapping teams cultivate robust findings that tend to persist. Centralized fields tend to find fragile facts, again, from my cases. Abnormal, improbable audiences drive biomedical outsider attention, biomedical attention in advance. Common audiences drive the most activity in the scientific space. And so that's all I have to say. I'd love, your thoughts, your pushback.
So any comments, questions, insights?
I just had a naive question about how you decide what, like, last year's most important medical problems are, in terms of the slide you had about how science builds its own narrative and isn't reactive. Because is it stuff that's like most in the news, or wouldn't, in some sense, why wouldn't all medical? If you look at the long term, to some extent, maybe there's a new disease here and there, but isn't a lot of medical health harm kind of not changing that much over long periods of time? We have, the same diseases, the same problems.
Well, the population's getting older and younger. Yeah. When the population gets older, then you get older person's diseases. You get musculoskeletal disorders. You get cancer, which are disproportionately represented by older persons. You have, so I would say there's a lot of change with respect to, if you were taking...
From one year to the next?
Yes. Yeah, with respect to, well, I mean, there's a marginal change from one year to the next. We're looking over a mid-range period to look at that, to look at those dynamics. We see, for example, in the U.S., that old person's diseases are much, much stronger, right, in their attraction of, and we can trace this through NIH earmarks from the 80s through until earmarks were erased in 2011. So one of the things that we see, how do we measure this? I'm certainly open to better ways of measuring it. We do it in a couple of ways. One, we do it through, Britain's Disability Adjusted Life Years Association, for up to 200 diseases, 115 diseases in its first iteration, and 200 plus diseases later. And then we correlate that with an indicator which is much more pervasive, which is insurance reimbursement costs, which ends up capturing about 30% of that variation. Which is to say, when we pay a lot more for these things, it captures about 30% of the dollars for those that we have. But of course, that captures 14,000 some odd disorders. So that's what we're looking at. I know for a fact that we have some measurement problems, which is to say that some of the disorders that we haven't represented as being linked are in fact causally linked. And so I think there's a lot to do to really clean this up to become. And I would also say that I don't think that would be like good marching orders for NIH to say, oh, we've got these gaps, you're not filling them, let's fill them. Because I would say maybe the most striking example is not in biomedicine, it's in something like, Japanese earthquake prediction. So that represented about a third of investments in basic research in the first half of the 80s. And it arguably had no influence or no improvement in prediction. So it was a hard problem. They didn't know how to solve it. They poured money into it. It was stupid. And so I'm not proposing that we basically give to NIH, oh, here are gaps that you're missing. But I would say that's the first stage towards actually providing an audit. So I believe that we can, right now we're trying to predict, okay, what's the likelihood that if you put concentrated or unconcentrated money into areas that feed into other areas. So we're trying to predict bottlenecks and these kinds of things where you can ultimately, now we're talking about this not as a diagnostic instrument, but as a technology, right? How could you actually rewire scientific and biomedical attention in ways that optimize the investment of these research dollars? And I guess what I'm saying is I think there's enough signal there that we could certainly do better than the kind of, the news driven and personal connection in the Office of Management and Budget kind of driven process that we see today. So, but those are the two measures.
I think we have time for one or two more questions, Thomas. So I think you were next, and then yourself.
Okay. At the beginning of your presentation, you mentioned interdisciplinary teams. Can you articulate more about that?
Right.
You said that if I properly understood, you don't trust.
No. I just basically there is a teams literature. The teams literature is basically, here's a very critical, sober assessment of it. Go big teams. Yeah, like that. Like that's the literature. I'm serious. There's like 100 papers. That's and so I think of course the big teams do important stuff. Like you couldn't have done LIGO without a large scale team. It required political conservativeness to get the resources, to get the sensitivity to the level that it did. I'm not, but the idea that all good science is done by large integrated teams is the narrative that has emerged, and I'm highly critical of that narrative. I think it's fundamentally wrong. I just don't, and I'll argue with anybody. I don't see any evidence on the counter side that when you can perform multiple experiments, that actually setting them up in competitive ways that facilitates diversity in the priors of expectation and in the methods. That being said, if you look at, and I didn't talk about this, if you look at the range of elements that large teams that draw together people from disparate places, so from disparate disciplinary backgrounds, which we kind of certainly wasn't our focus here, but it's a great question. You do see, like necessarily some increase as you have more in the diversity of the citations, right? So if you were to look at like maximum combinatorial novelty across these papers, you see basically from like members 1 to 6 an increase, and then a dramatic decrease that at about 10 people drops far below 1 person. So I would say that clearly if if what you want to do is do this, is basically mash together contexts, then you might need people from disparate spaces. But again, what we also see is that you have like kind of a high brain to muscle ratio that activates that, which is to say when you have like 2 or 3 PIs and like huge labs underneath that, it's actually very unlikely that those elements get combined into what looks like a kind of a novel combination of contexts. Where you have 2 or 3 PIs with very few labs, they're not supporting those persons, then you see a much higher return on surprising contexts for surprising backgrounds. And so that's kind of what I meant, that we're just starting to investigate, what basically the career histories look like lined up with these novel contexts, because those are also, they could be certain kinds of novel teams, and we haven't wired all that together. But it's a great question.
A minute or two after 2, so we're going to spend the next hour before we end at 3